perpendicular from P upon OQ, and let that perpendicular is denoted by PL. So PL is the perpendicular. See, this is a curve actually, but then this is the neighborhood of P. This can act as a straight line also. If it is very close to P, this is the neighborhood, it will be very close to P. Let me suppose that this angle is alpha. I have to show that I have to find the angle between tangent and radius vector. That is denoted by phi. I have to show that tan phi is r d theta by dr. This is the article. Or phi is tan inverse r d theta by dr. What I have done? I have taken a point PR theta on this curve. This is r, length between the pole and up to the point. This is r. Theta. Theta is angle between this radius vector and this initial axis. I have taken a point Q which is neighborhood of P, r plus delta r, Q, theta plus delta theta. These are the points. Accordingly, this will be r plus delta r. I have drawn a perpendicular PL upon OQ. Okay. Now from this triangle, from the triangle PQL, what is tan alpha? Perpendicular by base. This is perpendicular PL and your base is QL. But your QL, it can be written as OQ minus OL. Fine. This is QL. This will be OQ minus OL. But what is OQ? OQ is the radius vector r plus delta r. So PL is r plus delta r minus OL. This is 1. You have tan alpha is PL upon r plus delta r minus OL. There are two unknowns, PL and QL. I will find out these PL and QL. I will get that tan phi, the angle between tangent and radius vector is r d theta by dr. Now from this triangle, from triangle PLO, I have sine of del theta. See, del theta is the angle. PLO or POL. Okay. What is sine del theta? Perpendicular by hypotenuse. PL by OP. But your OP is R. So your PL is R sine del theta. Again from the same triangle, cos del theta is base by hypotenuse. This is the base OL upon OP. This is OL upon R. So OL is equal to R cos del theta. Now I know what is PL, I know what is QL. Let me substitute in 1. Now from 1, tan alpha is PL R plus delta R minus OL, which is R sine del theta R plus del R minus R cos del theta. This can be written as R sine del theta del R plus R 1 minus cos del theta, or this is equal to R sine del theta by del theta. Let me divide and multiply by del theta, del R by del theta, or twice sine square del theta by 2. 1 minus cos theta is twice sine square theta by 2. That is the formula which I have used. So this is equal to R sine del theta by del theta. Then you have del R by del theta. Then sine square del theta by 2 divided by del theta, because I have divided and multiplied by del theta both. And this 2 I will bring it here. Now let me take limits as del theta approaches 0. See, when del theta approaches 0, your Q will approach to P. Q approaches to P. When Q approaches to P, then this alpha will approach to phi. Alpha will approach to phi. What I will get? I will get from 2 tan phi. Instead of alpha, I will get phi. When Q approaches P, let me put it like this. Q approaches P, alpha will approach to phi and del theta will approach to 0. Fine. I will get, this is R, limit theta approaching 0, sine theta by theta is 1. This is dr by d theta, and this is 0 because this will be r twice sine square del theta by 2, and again sine del theta by 2, which is 0. So I will get tan phi is r d theta by dr. So the angle between the tangent and radius vector is given by r d theta by dr. This is the first article. Now let me take one more article, or let me find the angle of intersection. See, you have seen that if this is the curve r equal f theta, this is the point p r theta, then this is the pole, this is the length between pole and radius, the point, and this is known as r. Okay, then if this is the tangent to the curve at p, then this angle is phi. Fine. And I have seen that angle between tangent and radius vector phi is given by phi equal tan inverse r theta by dr, or tan phi is r d theta by dr. Now on this curve, on this point rather, let me intersect one more curve. This is the curve, say some another curve r equal function of the r f theta. There will be one more tangent to the curve at this point, and there will be one more angle between the radius vector and tangent. Say this is phi. If I have taken this phi or phi 1, this will be phi 2. You can see that phi 2 is angle between radius vector and the tangent. Phi 1 is angle between radius vector and tangent. This is tangent to the first curve, this is tangent to the second curve. But something is common there. This portion is common to both. This is angle between radius vector and tangent, this is phi 1. Angle between radius vector and tangent, this is phi 2, and this thing is common. This thing is denoted by alpha, the angle of intersection. This will be phi 2 minus phi 1 if phi 2 is greater than phi 1, or this will be phi 1 minus phi 2 if phi 1 is greater than phi 2. Fine. Now let me take, you have already done in your 12th class, length of tangent, subtangent, normal and subnormal. I will also find that point. This is another article, the lengths of tangent, subtangent, normal and subnormal to the curve r equal to f theta. Earlier you were finding these lengths for the curve y equal fx. Now we are finding it for y equal f of theta. You see, let this be the curve r equal f of theta, and this is the point pr theta. Okay, this is the pole O, then OP is equal to R, you know this. Let this be the tangent to the curve at P. You have seen that this is tangent to the curve at P, this is the radius vector, and this is the angle phi between tangent and radius vector. Fine. Okay. Now let me have this point. From this point, let this be the normal to the curve at this point P. Say Pn is the normal. Fine. So this angle is phi, you know, angle between radius vector and tangent. This angle is this is normal, so this whole angle will be 90, but this angle will be 90 minus phi. Okay. Now let this line be perpendicular to OP, which meets tangent at T and normal at N. Fine. Then you know this is polar tangent PT. This is polar subtangent. This is normal, polar normal, and this is polar subnormal. Fine. Let me again explain this so that you will not get confused later. This is the curve r equal f theta. This is the point PR theta. This is the pole. This is r. This is the tangent to the curve, and this is phi, angle between tangent and radius vector. Fine. Since this is the tangent, this is the normal. Normal is always perpendicular to the tangent, so this is normal. Fine. Now I am drawing a line which is perpendicular to OP, which meets normal at N and tangent at T. This PT is polar tangent, this is polar subtangent, this is normal, and this is subnormal. This is polar tangent, polar subtangent, polar normal, and polar subnormal. Okay, now let us come, and I have told you that this whole angle is 90 because this is normal to the normal to the curve, and this will be 90 minus phi. Now let me take this triangle. Angle is phi. From this triangle, let me find sine and cos. Sine phi and cos phi. Now, from the triangle, let me put it here so that you will also see what I am taking. From this triangle, triangle TOP. What is sine phi? This is perpendicular by hypotenuse. Perpendicular by hypotenuse. OP by PT or TP. But OP is R by PT. So I have PT equal to R by sine phi. This is R cosecant phi. Okay? But cosecant phi, you know, it is 1 plus cot square phi. This is R 1 plus 1 upon tan square phi. But you know, tan phi is R d theta by dr. So this is R 1 plus 1 upon r d theta by dr whole square. So our pt is r 1 plus 1 by r square dr by d theta whole square. So length of polar tangent, pt is r 1 plus 1 by r square dr by d theta whole square. Fine. Similarly, from this triangle, cos phi, base by hypotenuse, base is ot, base is op. Okay, from this triangle only. From this triangle, let me find cos phi. Base See, from this triangle, sine was some perpendicular by hypotenuse. Perpendicular by hypotenuse, and your cos is base by hypotenuse.